Okay, picture this. Fast, futuristic networks with glowing data streams crisscrossing a digital planet, processing literally millions of transactions in the blink of an eye. Sounds amazing, right? But what if I told you the absolute biggest breakthrough in blockchain scalability isn't actually happening inside Ethereum, but beneath it? Every single day, millions of Rollup transactions are making crypto faster and way cheaper. It honestly gives the impression that the whole scalability problem has finally been solved. But there's a catch. Hidden right beneath every Rollup is a critical dependency that almost nobody ever thinks about. As we dive beneath this visible layer, there's an entirely new infrastructure carrying enormous amounts of transaction data. So today, in this explainer, we are going to uncover the mystery of data availability, the invisible foundation that will literally determine whether the entire modular future of blockchain succeeds or fails. Before we jump into it, please note, this video on the channel Blocks, Bonds, Funds is created for educational and informational purposes only and does not constitute financial or investment advice. All right, let's dive into this. To really understand why we even need this hidden layer in the first place, we have to look back at the massive scalability problem that early blockchains faced. Just visualize the rapid growth of blockchain adoption for a second. Millions of new users flood the network, right? The blocks get hopelessly congested, transaction fees skyrocket to just absurd levels, and the entire network basically starts to overload, making everyday usage nearly impossible. This is what we call the classic blockchain trilemma, that inherent tension between decentralization, security, and scalability. Monolithic architectures like Bitcoin, which handles roughly 7 transactions per second, or early Ethereum, they constantly struggle to balance all three. I mean, when every single node around the world has to process, compute, and store every single piece of transaction data, you hit a fundamental mathematical bottleneck. It just cannot support global demand. Contrasting the old paradigm with the new really shows us the fix here. On the left side, we have monolithic architecture. It's a super rigid system where execution, consensus, data availability, and settlement are all crammed into one single layer. Think of it like having one single employee cook the food, serve the tables, clear the dishes, and wash up at a really busy restaurant. Eventually, no matter how fast that person is, the whole system is going to choke. Now on the right side, we have modular architecture. This is a highly adaptable, modern approach where those 4 functions are split up into specialized layers. By decoupling these responsibilities, networks can finally break that bottleneck, and it opens the door for some unprecedented scalability. This powerful shift to modularity gave rise to Layer 2 scaling solutions, which execute transactions completely off-chain. Let's look at optimistic rollups first. Instead of doing all the heavy computational lifting directly on Ethereum, these rollups process thousands of transactions in a separate environment. They bundle them all up into massive batches and then post periodic state commitments, which are essentially tiny cryptographic snapshots of everyone's updated balances back to the main Ethereum chain. They assume these transactions are valid by default, optimistically. But if an invalid transaction somehow slips through, there's a specialized challenge window where people can submit a fraud proof. This is a brilliant way to bypass the base layer congestion, dramatically increasing throughput while still piggybacking on Ethereum's ironclad security. And it's not just optimistic rollups doing this. Zero knowledge or ZK rollups take a slightly different approach. They compress these massive batches of transactions into highly complex mathematical validity proofs before sending them over to Ethereum. These cryptographic proofs essentially guarantee that the math checks out perfectly. But here's the catch, and this is absolutely crucial, because it's the exact moment where the entire system can unravel if we aren't careful. Those proofs, whether they're optimistic fraud proofs or zero-knowledge validity proofs, are completely useless if the underlying transaction data isn't publicly accessible. The proofs verify the math, sure, but the raw data verifies the reality. Without the raw data, the proof is basically just a lockbox with a missing key. So, you might be wondering, what actually happens if that data is just hidden? Imagine a blockchain that reaches consensus, finalizes blocks, looks completely secure, yet literally no one can verify the data behind those transactions. Suddenly, that core trust just starts to disappear. If execution isn't the real bottleneck, what is? Well, it's the ability to actually see and verify the data. This terrifying scenario brings us to a critical threat known as a data withholding attack. Let's picture what this actually looks like in practice. If a malicious rollup operator successfully hides the underlying transaction data, users completely lose their ability to challenge fraudulent states. They can't reconstruct the chain's history, and even worse, you might not even be able to compute your own balances. Without that crucial data, you could literally be locked out of your own assets. The consensus mechanism might loudly declare that the block is valid, but without the data to back it up, it's a total breakdown of the trustless ecosystem. You're forced to blindly trust the operator, which, let's be honest, entirely defeats the whole purpose of blockchain. And this is exactly why data availability, or DA for short, is the absolute non-negotiable foundation of blockchain trust. Let's quickly break down why it's so critical. It really revolves around 4 fundamental pillars. First up is security. Users need to independently verify transactions so no single entity can cheat the system. Second is integrity, ensuring the network state is correct and totally resilient to malicious modifications. Third is functionality, guaranteeing that validators have the exact data they need to actually process and validate the rollup at any given moment. And finally, interoperability, allowing consistent, frictionless data access across multiple overlapping networks. When transaction data is published, distributed, and stored correctly, anyone trying to reconstruct the rollup state can do so with perfect clarity. To fix this vulnerability, we really have to rethink how blockchains are built. And this brilliantly illustrates the 4 core functions at play here. You've got execution, which is where the actual transactions are processed and computed. Settlement, which acts as the ultimate source of truth and dispute resolution. Consensus is the mechanism for agreeing on the chronological order of those transactions. And finally, data availability. This is the absolute guarantee that the underlying data is published, distributed, and accessible to everyone. By actively splitting these 4 integrated functions into specialized, separate layers, blockchains can achieve dramatically greater scalability. You're no longer forcing every single node to do every single job. The network just becomes a finely tuned modular machine. Now, because execution is no longer the real bottleneck, crypto's top engineers are building entirely new networks purely dedicated to data availability. These layers operate silently right beneath existing blockchains. Take a look at EigenDA, for example. Instead of a traditional blockchain, it uses a massive decentralized storage grid. When Rollup sequencers bundle up their transactions, they send their data blobs directly here. These EigenDA nodes are strictly obligated to store those data fragments and provide them instantly upon request. They're essentially acting as dedicated, high-performance infrastructure providers for the entire modular ecosystem. Another major player completely transforming the space is Celestia. Celestia takes this incredibly unique approach by completely removing the execution layer from its architecture altogether. It doesn't run complex smart contracts, and it doesn't compute user balances. Instead, it focuses purely on ordering transactions and making sure the data is widely available. By completely stripping away that heavy, computationally expensive burden of execution, Celestial drastically reduces the hardware costs required to run a node. This allows almost anyone with a basic computer to participate in securing the network, providing a pristine, highly decentralized data layer for rollups to seamlessly plug into. And then we have Avail, which focuses really heavily on empowering light clients. If you're not familiar, light clients are basically lightweight nodes that don't need to download the whole massive terabyte-heavy blockchain history. DA layers like Avail utilize some incredibly advanced cryptography, so these light clients can independently verify that transaction data is fully available in a trust-minimized way. And they can do this globally without ever having to rely on massive, expensive full nodes or central authorities. But how exactly do these networks pull off this magic without forcing everyone to download terabytes of data? Well, the answer lies in a brilliant cryptographic breakthrough called data availability sampling, or DAS. It allows nodes to verify huge data sets almost instantly, and it works in 3 really elegant steps. First, something called erasure coding actually expands the original dataset. Second, that expanded data is systematically broken down into tiny, manageable chunks. And third, nodes and light clients across the network conduct random sampling. They request just a few of these tiny chunks at random. If enough of these random samples are successfully retrieved by light clients scattered all around the globe, the network can statistically prove with near 100% certainty that the entire block of data is available to absolutely everyone. Now, the real magic here happens in that first step, erasure coding. This is an advanced data protection and recovery mechanism that expands the original dataset by infusing it with mathematically redundant pieces. It's kind of like a holographic image. You know how if you drop a hologram and it shatters into pieces, you don't just get a tiny, unrecognizable fragment of the picture in each shard. You can actually still see the whole picture reflected in the broken pieces. Because of erasure coding, the original data block can be completely reconstructed from just a small subset of the fragments. This ensures the transaction data is entirely recoverable, even if malicious actors try to hide, delete, or withhold major parts of it. Not to be completely fair and look at the whole picture impartially, relying on external separate DA layers definitely introduces its own potential risks. When you transfer data from one zone of sovereignty to another, you often have to rely on cross-chain bridges. If a dedicated DA layer were to ever suffer a 51% attack, honest users naturally wouldn't follow the corrupted chain, but the attackers might actually be able to manipulate the DA attestation data that gets stored in the bridge contracts back on Ethereum. While orchestrating an attack of this magnitude would demand considerable resources and vast capital, cross-chain bridge exploits are a known vulnerability in the industry, and modular architectures have to navigate them really carefully. But even with those calculated trade-offs, the ecosystem transformation we're witnessing right now is absolutely breathtaking. Layer 2 rollups, application-specific chains, and entirely new modular networks are increasingly plugging directly into these specialized DA layers. As a result, we are seeing exponential scalability unlock across the entire landscape. It's driving down costs, it's speeding up finality, and it's doing all of this while maintaining incredibly robust security guarantees. Data availability has silently become the invisible infrastructure of the modular future. It's solving the deepest, most complex bottlenecks of modern blockchain technology. Which brings us to a pretty powerful realization. As we journey beneath the surface of Ethereum, beneath the rollups and the smart contracts, we find the real truth about scalability. The future of this entire ecosystem relies entirely on who controls the availability of the data itself. The most important layer of crypto might just be the one you never see. Thank you so much for joining me on this explainer. I want to leave you with this to ponder. In a completely trustless digital world, how confident are you in the data that you can't actually see?